I just have that was the long list of other things that you shouldn't have.
I don't know that.
How you play the way how they use they went through so taking notes I mean, I think but I'm like 50 now, my girlfriend. The guy I have, like, is there a problem? Then the problem was one of the aerospace insurance company.
He was ready for a job.
Oh, that's good.
Nothing to do with engineering, but
What's it for?
that's for the city of Vernon utilities operational training.
Okay.
He gets back there tomorrow.
Yeah, that's good.
So I gotta email me to test this.
Okay. We have to take a test to, okay.
My cousin works, or I've got two cousins that work there, and one of them texted me today. Hey, I got information for you. He's like, it's 100 questions.
Okay.
That's,
Like, it's almost like a weeding tool then, like who's gonna put up with 100 questions, right?
Yeah. And he's like, read up on homes, wow, yeah, vehicles that are. Okay. He's like, know what a lot is. And mega watt. Yeah. He's like, okay, fine. He's like,
That's good.
He's like, there'll be a lot of uncritical thinking. We had all day long.
Yes, you do.
So I am not worried.
That's good. Is it, do you have to do it live or do they just give it to you and then
I
just email back?
I would go and
I'll go in live. Okay. Now that makes sense.
works out. We may not have to miss any school forward. Cause that's coming up.
Well, so I don't think well, for the faculty at least, we're not going to strike this semester.
What I saw was the week after this break.
It's only going to be select campuses. So Fullerton was not selected as one of the striking campuses. Yeah, we'll see. We'll see.
And then there's the skilled trades worker.
Yeah, they're striking next week
On Tuesday.
Yeah, it's important for us. I think, yeah, I don't know if a machine shop pricing is fun, but
Yeah, we gotta fix that, water main leak outside.
yeah,
It took them almost 2 weeks to shut the water.
Yeah.
To begin with, and they just dragged it out.
yeah, it's very clear what they're
The
doing.
dorms
Yeah.
are without water.
Oh, really? The dorms don't have water?
Yeah,
Oh, wow.
that's why there's the, trailers outside.
Oh, I didn't realize that's what
And
they're
then,
for.
the old dorms, they have a hose hooked up to the fire hydrant
Uh-huh.
running in.
Wow.
Wow, someone did a bad planning of setting that all up.
Yeah, wow. Oh, I didn't know that.
Oh, yeah.
I'm annoyed because where that water line is, that's where I usually access the park. Now I gotta go all the way around. Yeah, and they sent us an email like, oh, it'll be fixed by Sunday, November 5th. I'm like, no, it's not.
No.
Just stop lying. Yeah, yeah.
That's the difference between paid by the hour and paid by the job.
Yeah. I checked on Monday, this week, like, oh, it got worse.
Yeah, originally was coming out from the, light post.
Yeah,
I saw
Yeah.
that one.
yeah.
Well, that's a new one. Never thought I would have seen that in person.
No, good for them. Good for them. For their strike.
Kind of saw that one coming, because SAG-AFTRA and, your, WGA and then the auto.
Yeah.
It's a trickle down effect.
Yeah.
They all, when one goes, they all have.
Oh, yeah. It's the year of strikes. It's a very.
So I actually took screenshots of all my grades.
Okay, that's good.
I'm gonna do it right before we go on Thanksgiving break.
Yeah, I mean, for me, I'm not, I mean, we'll finish the semester no matter what. I mean, and the good thing for us is that we have a little bit more stuff to do after Thanksgiving, but after that week, the class is basically done. So the last week, at least for these two courses, for the optimization FBA, it's just gonna be just work on your final project and stuff. But I'll be available, if anything virtually, then, if we're striking. Yeah. The thing I'm worried about is that week is the week before my wedding. So my wedding is December 9th, so it'll be a very hectic week. So if I'm not available that week, it's not because I'm striking, it's because I'm planning a wedding.
Sure.
Hey, I've been saying it since the beginning.
We're just leaving the contact, not the body interaction.
Exactly. Yeah, just the contact.
I'm getting.
Hmm?
I'm trying to get.
Yeah, no, go for it. Because we want the car to be able to bounce, basically. So.
No, that.
All right, it's 5:30. Let's go and get started. Right, good evening, everyone. How's everyone doing today? Hanging in there. Got one more week and then Thanksgiving. So it's gonna be a really busy week next week, but still one more week, and so we're almost there. Okay, so it's been a while. So it's been a while since we've done an ANSYS activity, just because we've been doing all the theoretical stuff. But this is the next one. This is also gonna be the final one for credit, I should say. Okay. So this is the last activity that you're going to turn in for credit. We have one more activity after Thanksgiving, right when we come back, but that one's going to be optional, and so that one's going to be more just for your own knowledge, and that one's going to be based on modal analysis and vibrations, and so we'll learn how to do that in the final activity. But this is the last one you'll actually turn in. Okay. Okay, and so we've been talking about this for the last 2 lectures, and so the subject for this activity is going to be dynamics, right? And so you can kind of see a little bit of an image here of what we're going to do. So we're going to be simulating a car crash, right? And so we'll be simulating a car, we'll be ramming it against this wall, and we're going to see how it's going to deform. I will admit it's going to look a little bit weird because we're going to be assuming a purely linear material, and so it's not going to form in the way that you might think. We're not going to have any kind of buckling or any kind of actual deformation of the car. It's just kind of hit it and it's kind of just jiggle. You'll see. But it'll still be cool nonetheless. Okay. Okay, and so you guys know the drill at this point, and so if you haven't already, go ahead and start up ANSYS Workbench. It takes a couple minutes to do so. Okay, and so while you guys are starting up ANSYS Workbench, I'll give a little bit of introduction on the activity, and then we'll get started. So in terms of length, this activity is definitely shorter than than activity 4. But because the dynamic simulations take a while, you're going to be just kind of sitting there and just watching ANSYS run for a good amount of time today. Okay. Okay. Any questions I can answer before we get started for today? Yeah.
Is the optional activity the grad student assignment?
It's not. It's going to be part of the grad student assignment. Will be part of the final project, and so we'll talk about the final project after Thanksgiving. Yeah. Yeah. You guys have enough on your plate. So ANSYS activity. Problem set and midterm, so I didn't want to overload you guys to the final project just yet. Oh yeah, and so what you guys will notice that the due date for this activity is not until after Thanksgiving, and so it's going to be Tuesday, November 28th, and so that's the Tuesday we come back from Thanksgiving. All right, any other questions before we get started? Okay. All right, so this is the activity here, and just like before, not only you need to start up ANSYS, but make sure you go to Canvas and download the CAD file. Okay, and so the CAD file here, I'm giving you 2 options, just because I think one year I don't know if it's just the version of ANSYS that we were using, but some people had trouble loading the file, and so I have both an IGS version and a step version of the CAD file. You only need one, so we're only going to use one, but if one of those doesn't work, then just check the other one. But for most people, the IGS file should work. But if you're having troubles or errors loading it, then you can use the step file, and that should be fine. Okay. Okay. So let's talk a little bit about the activity. Okay. And so just like we mentioned before, we're going to be using the explicit dynamics package within ANSYS. And so we talked on Tuesday about kind of what this is. Okay. And we're going to be using it to simulate this car crash. Okay. And so hopefully you guys have opened up ANSYS already. And so from ANSYS Workbench, we're going to load in the explicit dynamics module here. Okay. And so from the left-hand side, you're going to go to explicit dynamics. You can double click it, or you can just click and drag it to the center schematic there. Okay. All right. And just like before, we're going to right click on geometry. We're going to import a geometry. Okay. And you're going to import the car crash CAD file that you hopefully have downloaded from Canvas. Okay. Okay, and so hopefully, if as long as the geometry works, it should load without any issues. Okay. All right. So first thing we're going to do before we jump into ANSYS mechanical is we're going to add new material properties, okay? Because according to the project specifications, the car that we're going to be using is going to be made out of aluminum, okay? So we want to make sure that we add that. Okay, and so hopefully you guys remember how to add a custom material property. And so to do that, we're going to double click on engineering data, okay? We're going to open up the engineering data sources. And so we're not going to add a custom material here. We're just going to use one that's within the ANSYS database, okay? So click on this button right here called engineering data sources. It's near the top, okay? And then what you're going to do, so it should be under general materials. And so let me go ahead and close this so you can see, okay? Where's general materials? I always have trouble finding it. There it is, general materials. Thank you. Okay, so under general materials here, these are kind of the general kind of standard materials for structural mechanics here. And so we're going to add two materials. And so on the one hand, we're going to add aluminum alloy. Okay, so that's a standard alloy for aluminum. And so it may not be exactly the type of aluminum that we want, but it's going to be pretty close. Okay. So we're going to go ahead and click on the plus sign here. And so after you click on the plus sign, the aluminum alloy, should be added to your project. Okay. And then the other material that we're going to add is down here, and we're going to add polyethylene, right? And so this is going to be just for fun. And so, we're going to see kind of how our results are going to change if we have a plastic car. Okay. So let's go ahead and add that to the project as well. Okay. So you should have three materials overall. So you should have structural steel, you should have polyethylene, and you should have aluminum alloy. Okay. All right. Any questions on that so far?
Oh, yeah, I don't have a window copy with the other materials.
With the other materials, you may have to reset the view. So maybe if you go to did you click on engineering data sources here?
Yeah, and then general material.
And then, but this window here is not here. Okay. Let's see. You could try either reset workspace here or reset the window layout. Or it might be one of these as well. And so I think you might have to do outline. Yeah, so you click view and then outline, and then that should show the list of materials at the bottom. Yeah. Okay. I'll come back to you, Chris, as you know.
Yeah, got it.
Okay. And so if for everyone else, if you've added the materials, let's go ahead and open up ANSYS Mechanical. Okay. So let's go ahead and exit out of this and double click on model. Okay. And so what this is going to do, this is going to open up ANSYS Mechanical, and it's going to give us open up kind of the main window that we're going to use for today. Okay. And so once you open up ANSYS Mechanical, you should see a window like this. Okay. And so you can see our geometry here. We have two parts of our assembly. We have one part that consists of the wall. Okay. And so that's part two. And then we have a separate part here for the car, and that's going to be part one. Okay. Okay. And so we're going to go through the standard procedures of setting the mesh, the boundary conditions. And what you'll see is we're going to have some extra steps for the dynamic simulation. Okay. But the first thing we're going to do is we're actually going to eliminate the connections in between these two parts. Okay. Okay. And so we can see that, just like any assembly that we've loaded in ANSYS, right? Because these two parts are very close to each other, they're basically already touching. ANSYS has created kind of a standard kind of connection between them. Okay. And if you click on this contact region in between the two parts, right? So you go to connections, contacts, and contact region, right? You can see from this setting here that it's set these two parts to bonded. Okay. And so right now the front of the car is basically welded together to the wall, right? And that's only just because ANSYS doesn't recognize this as a car crash simulation. And so all ANSYS sees that these two parts are really close together, and so we should bond them together just to make sure that they stay together. Okay. But of course, we don't want that. We don't want our car to be bonded to the wall. And so we need to eliminate this contact region. So you're going to right click this contact region, and you're just going to delete it. Okay. And so deleting it will just make sure that the two parts are no longer have any connection, right? The car is free to hit the wall and bounce off, which is kind of what we want, right? And then we can go from there. So before we move forward, make sure you delete this contact region between the car and the wall. Okay. Okay. All right. So now that the connection is eliminated, let's go ahead and specify the material properties for our two parts here. Okay. Okay. So we have two parts here. We have the wall and we have the car, right? And so for the wall, we don't really care what's happening with the wall in this case. The wall kind of only exists for us to hit it, basically. So the wall is not really going to deform all that much, and it's not expected to, to deform in any kind of realistic way. And so we're going to keep the wall as steel, right? I guess if you wanted to be more realistic, you could make a concrete wall, but steel, concrete, it's all going to be the same thing. Okay. The one that we mostly have to change here is the car, right? And so the car, we're going to change it from structural steel, and you should be able to change it to aluminum alloy, right? So we'll do the simulation with aluminum first, and then we'll do the simulation with plastic after that. Okay. Okay, so let's go ahead and switch that to aluminum alloy, right? And so now we are ready to go. All right. So first thing we're going to do is we're going to mesh, right? And so we need to mesh the wall. We need to mesh the car. Okay. So let's do this. And so let's add two method objects. Okay. And so one method object is going to be for the wall, and the other method object is going to be for the car, right? So let me go ahead and rename these just so you can see. Wall method. This would be for car method. Okay. Okay. And so the main thing that we have to change here is the element order. Okay. So normally, because this is a structural simulation, we want to set the order to quadratic, right? Just because that's generally what's going to lead to more accurate results. It's going to also prevent shear volume. Okay. But for dynamic simulation, this is the only time in the class where we're going to do this. We're actually going to switch the element order to linear. Okay. And the reason for this has to do with the cost of the simulation. And so because dynamic simulations are so expensive, we have to kind of switch to a linear order here to make sure that we kind of reach convergence in a reasonable amount of time. Okay. So we're going to set our element order to linear for both the wall and the car. Okay. Okay. Next thing we're going to set is the size. So let's go ahead and create sizing objects for both the wall and the car. Okay. So let me go ahead and rename these. This is wall sizing. And this one right here will be car sizing. Okay. Okay. So now we need to set mesh settings for the wall and the car, right? So the car is going to be where most of the action is going to be taking place, right? So the car is going to be the one that's going to be primarily deforming. It's going to be the one that's going to be under stress, okay? And so you want to make sure that you have a good mesh density for the car, okay? For the wall, the wall is not really going to do much here. So we can actually make a very coarse mesh for the wall, okay? In fact, you want to do this because you want to make sure that you have as much mesh density in the car as possible, okay? So I'll let you guys play around with it for a little bit, but let me kind of give you an example here. So let me set this to 0.2. Maybe set the wall to 1.5. You don't have to copy my exact numbers, and so if you missed it, then don't worry about it. Okay. Okay. So something like this is looks good. Okay. And so you can see here the wall is fairly coarse. Okay, so we don't need a lot of mesh density there. But for the car, we have a fairly fine mesh. Okay. In fact, let me do this. Let me see if I can do hexes on this one. Sometimes the hexes work, sometimes they don't. We'll see if it works for this one. All right, so I'll give you guys a couple minutes, play around with the mesh settings, but you should have something that looks, relatively well refined like this, right? So your car should have a good amount of density and your wall, not so much, okay? All right, if anyone's having issues, with the UI or anything like that, just raise your hand and I'll come around it at this point. All right, how's everyone doing with the mesh? Everyone able to get a mesh? Okay, all right, so let's go ahead and move on. Okay, so now that the mesh is complete, the next step is to apply loads and constraints, okay? So there's actually not much to do here. So most of the loads are going to be from the motion, okay? And so we're actually not going to apply any explicit forces or any kind of explicit pressures in this case, okay? The only thing that we have to add here is we have to add a fixed support for the wall. So just to make sure that once the car hits it, the wall is not going to go offline to infinity, okay? Okay, so let's go ahead and add our fixed supports, okay? Okay, so you're going to right click on explicit dynamics A5, and you're going to go ahead and add a fixed support, okay? Okay, and we want to fix the wall here, but we have to be a little bit careful about how we apply this fixed support, okay? You don't want to apply the fixed support on a surface like this, okay? Because this is the surface that's actually going to be contacting the car, right? And so, once the car actually makes impact with the wall, it's actually going to compress the wall a little, right? And that little bit of compression is actually going to be really important, just for kind of stability and kind of realism. Okay? So you never want to apply a fixed condition on a part, which is going to have an impact. Okay, that's going to cause some issues. Okay, and so we're going to fix the model around the wall. Okay, and so we're going to apply the fixed supports on all the outer edges of the wall, like that. Okay. And so that basically makes sure that the wall is not going to go anywhere after the crash, but also this front face of the wall is free to kind of indent and deform a little bit, okay? Which is going to be an important part of the simulation. Okay. Yes.
Why couldn't we just fix the back half of the wall?
You could do that as well. That's another option. So both are going to have very similar effects. Yeah, you can either fix the back side of the wall or the outer edges. Yeah. Okay. Okay. And so we're also going to apply another boundary condition on the car. Okay. And that's mostly just to make sure that the car doesn't kind of clip through the ground, right? So even though we're not simulating the wheels here, we're basically only just simulating just the shell. We want to make sure the car doesn't clip through the ground after it crashes, right? And so we're going to add a displacement boundary condition. Okay? So you're going to right click on explicit dynamics A5. You're going to go to insert, and then you're going to click on displacement right here. Okay. Okay. And so we want to, and so if we kind of, rearrange the geometry like this, we can see that the vertical direction for this geometry is in the Y direction, right? And so we want to make sure that the car doesn't kind of, displace kind of in this direction, right? Because normally that's where the ground is. And so we want to make sure that that doesn't happen. Okay. And so to do that, there are a few different ways you can do it, but the way that we're going to do it here is we're going to click on all the outer edges here of the bottom. Okay. Okay. So we're going to go around this entire bottom surface. We're going to click all of these bottom edges. Okay. Oops. Okay. We're going to click on all those bottom edges there. We're going to apply that for the geometry. So that should be 8 faces. Okay. And then after you do that, you're going to set the Y component of the displacement here to be 0. Okay. So the X displacement and the Z displacement, we're going to leave it free. Okay. Because that's going to allow the car to impact the wall. But we just want to make sure that it doesn't apply any displacement in the Y direction. Okay. So we're going to set that one to be 0. Okay. Okay. So let me go ahead and highlight that part here. Okay. So there are 2 boundary conditions that we're applying here. And so we need to make sure that the wall is not going to move. And so we need to make sure we apply our fixed support there. And then we're applying a displacement boundary condition on the bottom edge of the car, just to make sure the car is not going to clip through the ground during the simulation. Okay. Any questions on that? All right, everyone able to apply the 2 boundary conditions? You guys have a question over there? Okay. Okay, so the next step here, so normally kind of this is where we would be able to run the simulation, right? So for a static case, the only thing you would need is just the mesh and the boundary conditions. But here, we also need the initial conditions, okay? And so the initial conditions basically tell us kind of what kind of state the simulation is going to be at the beginning of the simulation, okay? Because remember the way that dynamic simulations work is that, we're solving this simulation kind of forward in time. And so, the next step is always dependent on what the previous step looked like, right? And so in order to do that, we have to define what the initial step would look like here, okay? Okay, so let's go ahead and define these initial conditions here, okay? And so this is a new menu here that wasn't present in our static simulations, okay? And so, but just like we apply boundary conditions, you're going to right click on initial conditions, okay? You're going to insert, right? And we're going to have one initial condition for the velocity, okay? Okay. Because the way that we're going to simulate the car crash is we're going to give this car an initial velocity and we're going to have it headed towards the wall, right? Okay, and so you're going to select the entire car geometry here, okay? So that's going to be your geometry for the velocity, right? And we want to apply that velocity in the negative X direction, right? Because the negative X direction is going to head the car towards the wall. Okay, so we're going to switch this defined by, so we're going to switch it to components, okay? And we're going to apply this velocity going towards the wall, okay? And so you want to make sure that your X component of the velocity here is negative, okay? Okay, so we'll give it just a sample value for now. And so keep in mind that the default settings here is in inches per second. Okay, so let's give it a default velocity of 5,000 inches per second. Okay, so we'll do minus 5,000 inches per second, which is not that fast. It's actually going to be not that fast. We'll see. Okay, so we'll start with that, and then we'll kind of play with that velocity as we go. Okay, so now that we have the initial velocity, the only thing we have to specify now is the analysis settings right here. Okay, and so the settings that we have to set here have to do with the time step. Okay, and so if you remember from class on Tuesday, we talked about when you're doing a dynamic simulation, you have to specify two things. And so you have to specify the time step size, and you have to specify the ending time for the simulation. Okay. So remember, in ANSYS, ANSYS is going to specify the time step size for you. Okay. The only thing you have to specify here is just the ending time. Okay. Okay. And so the ending time being, how much time you want the simulation to simulate. Okay. Okay. And so since we're simulating a car crash, it's all going to happen very, very quickly. Okay. So we don't have to set a high end time for this at all. And so let's set something really small, like 0.05. Okay. For this first one, it doesn't matter all too much, just because of we're going relatively slowly. Okay. Okay. So now that you have the end time, we have the mesh, we have the boundary conditions, we have the initial conditions. Okay. The last step here is just to run the simulation. And so before we run the simulation, we want to make sure that we specify our outputs. And so let's go ahead and put in our usual suspects. And so let's go ahead and put the total deformation. Let's go ahead and put the equivalent stress. Okay. Let's also add the equivalent strain as well. Okay, so we've got both equivalent stress and equivalent strain. Okay. Okay. And so with all of those results added, we're ready to run. So let's go ahead and click solve. Okay. And now you're going to be doing what you're going to be doing for most of today is just sitting around and waiting, because it's the simulation is going to take a while. Okay. So you can check the progress of the simulation in the bottom left corner of the screen right here. Okay. And so basically this progress bar is going to fill as the simulation finishes. But actually, let me show you something. So you don't have to just wait, and you don't have to watch Thursday Night Football waiting while this is going on. Okay. So let's go ahead and click on solution information here. Okay. And so after you click on solution information, what you're going to see here is a bunch of numbers. And so these numbers here indicate, how the simulation is going. And so if you're kind of savvy with trying to finite element theory and kind of what's going on, you can kind of read those numbers. Okay. But what I want to show you here is not the solver output, is I want to show you this energy summary. Okay. And so go ahead and click on energy summary. And what that's going to do is that it's going to bring up a graph like this. Okay. So this is pretty cool, because it's basically showing you all the different energies that are inside your system and how they're evolving as a function of time. Okay. In particular, you should look at these two energies here. So in the blue, we have the kinetic energy. Okay. So the kinetic energy is the energy of motion. Okay. And in purple here, we have something called internal energy. Okay. And so internal energy is the energy that's being kind of entered into the system as the car deforms, right? And so as the car deforms, the internal energy of the system is going to go up. Okay. And so what you're seeing here is that as the car kind of crashes into the wall, right, its kinetic energy starts to go down, right? Because as the car impacts the wall, it's going to start to slow down. In fact, it's just going to stop as it hits the wall. Okay? And then the internal energy is going up at the same time. Okay. Because as the car hits the wall, as it impacts the wall, the car is going to start deforming. Okay. And oops, looks like we have an energy error. Okay. Okay. So the energy was too large. Okay. Oh, that's cool. I've never actually seen this before. Okay, so we had an error here, and so the error was that the energy, the internal energy, I think, reached a little bit too big. So I think the deformations were a little bit too large. So let's actually lower the velocity here, and let's actually see what that's going to do. So instead of minus 5,000, let's set it to minus 500. Okay, so I'm going to rerun the simulation with a initial velocity of 500, and that should kind of help lower the total amount of energy in the system. Okay. Okay, so I'll let you guys play around with this for a little bit, but go ahead and try different velocities and different end times, right? And see if you can kind of get a result that looks like in the document. Okay, so I'll let you guys play around this for maybe like 15, 20 minutes. And then we'll kind of reconvene and kind of talk about the rest of the activity. Okay.
Mine keeps getting off.
Yeah, it should do that. And so it should kind of bounce off and kind of, kind of just almost kind of like wiggle back and forth. The simulation, it could take anywhere between, 2 to 3 to 5 minutes usually. Yeah. So if you're following the PDF, you'll see that I gave it a much larger velocity. So I think I gave it a velocity of 150 meters per second. So you can definitely do that. So you can go ahead and give that a try if you want. But I thought I'd try a lower velocity. It looks like that might not be working. Because I usually don't see this hourglass energy go up. But yeah, play around with it. See if you can kind of get it to converge. If this doesn't work, I'll try the numbers that I have in the simulation.
No, that's what you actually, if you use the results, so go ahead and put on well, it's still running, but basically what's happening, the R is getting the result, it's kind of like bouncing off the phone. So that's kind of what she kind of worried that might not happen. Yeah, it does happen very quickly. And so if you look at what I did, it's yes, so the initial impact is the first hit. It's up there, it's kind of like maybe the plate is kind of like this is kind of the vibration. Now, yeah, but this that's okay. This one is, yeah. Energy chart is very.
Yeah, it should do that. So you should start to see after the initial impact, you should see it basically vibrate. Okay, yeah.
Good, right?
Yes.
Up to this point, I've always had something go wrong.
Yeah. I'm gonna kill this one. Actually make this a little bit smaller. Let me change the units here. Yeah, what's up? No, that's what's supposed to be. So you should see basically what you should here. So so technically, most that happened right here. So this kind of initial dip right here, and then what all it's doing from here is just this is just vibration. And so the car actually can't like just because it's very so all we can do is basically vibrate. All that's happening right now is the car kind of hit it and bounced off and just kind of vibrated. But no, that's right. Yeah, and so the end time that was set here was actually very long. So you could kill this thing. So if you want to kill it, you can click on that. It's gonna take a minute. And you can set the time, any time, like 5 minutes.
We put our pictures in to the report, it doesn't matter where we have our card.
Doesn't matter.
I know you just grade them off of completion, but I don't want to.
Oh, yeah, yeah. Oh, that's good. Yeah, so I did a couple of things. So it might be an issue with with the hexahedral elements. And so you can try changing it to tetrahedrons if your mesh isn't text already. And then what I did was I increased the initial velocity. So I changed it to meters per second. And so I've changed it to -50.
-50.
Yeah, and then your end time here, you want to make sure this is actually pretty small. So reducing this to like 5 times 10 to the -4.
Okay, and if you think of the units, what's the unit for the car element size?
I did 7.5 times 10 to the -3 meters. So it changes to inches. It's about 0.3 inches apart. So.
Like 0.3 inches and what were the other units size?
And the initial velocity, maybe set it to be something around -2,000 inches per second. What's up?
I had a question on the first. I was kind of confused with this one. The trust and then how would it work? 'Cause kind of how I'm looking at it is, when I'm looking at this one, technically these have concepts.
Yep.
And these obviously solve for them. I'm kind of confused how you put them together. It's like I was looking at the notes and it's kind of confusing, like where you take this and then this is your K concept.
Yeah.
How do you plug in this?
So they all have the same degrees of freedom. So first of all, this is a lining problem. So you can save yourself a lot of work. Don't use this big one.
Oh, okay.
So you can just consider that.
Oh, it'd be that 2 by 2.
Right. And so even though they're different types of elements, they're still connected to the same node, right? And so for both the string and the truss element, you can see that they're both affecting D2 hits. And so those two will overlap in the assembly.
Yeah.
Just like
Oh, okay. Okay, let me take that. One else.
yeah, and so you know you'll see later on too. You might have a mixture of beam and spring element. And so the type of element that they originated from doesn't really matter. And so it's more just where they overlap.
Yeah.
Yeah, it overlaps. Yeah, so kind of the same general. Solving for the case. Exactly.
Exactly.
So if it helps, this is like the effect spring concept. And would you get a singular value for this? No. Work with me to leave it outside and then just add that back into them. That's fine. Usually when I have multiple elements like this, I just multiply through, just so I don't get confused.
Yeah.
So it's just whatever.
Yeah, 'cause I'll get confused with
Yeah. And then, it is by completion, but.
Yeah, I wanna make sure I do this right.
It's gonna be a lot easier. Then I'll. Basically right after you do that. And then on the exam, we do matrix multiplication, correct? No, so there should be no matrix, you shouldn't have to solve anything.
Yeah, I got to this point, but I'm like.
Yeah, so this is the ending.
Oh,
Once you apply the value, it looks like this would have any of the constraints. But you would apply like the constraints, and that would be the answer.
Oh, okay.
Yeah.
Yeah, 'cause I got it where I was, and I'm like, okay, cool. I want to have a question. So I want that.
Yeah.
So I do the airplane.
Yeah.
But now, I'm gonna add the vocal over on the airplane. I still want to add, identify the vibration. When the water.
Yeah.
Yeah.
Yeah, so we'll do that, after the break. So we're gonna do one more activity, it's gonna be on vibration. And so we'll cover that. If you want to preview, I do have the lecture notes online. So if you go to files here, I don't think I have the activity yet on
Yeah,
ANSYS yet.
I
but
just
do
want
have
to read
lecture
the.
notes. Yeah,
read
so
the
I can put the activity on there, so it's gonna be, well, so the lecture notes is gonna be 14, so this is kind of the lecture notes on modal analysis. And then, yeah, I haven't posted the activity, but I'll post that activity so you can take it.
And last one is told me that you want to apply the whole course on the whole, and you know that A6.
Yeah. Yes,
A6.
A6,
Yeah, I see, okay.
yeah, down here.
Yeah, okay. Yeah.
All right, thank you. Yeah.
Sorry.
Yeah.
You're in. Again, I.
Yeah, so the end time I have is one, well, I changed it a little bit, so I increased it a little bit, it's 1 times 10 to the minus 6.
Get this done early.
Huh?
We get this done early.
Yeah, no, this one's very short, it's a short. At the end of the semester, so you guys have a lot of.
I had 2 projects, 3 projects. One I got.
I have no idea how the optimization project. If the code works, it's very easy. Just do code, write the report. But if you struggle with it,
Take the wall, this is the NR one. Seems very straightforward. The big 25 bar would be. I think it's just flat out.
it's a lot of constraints, a lot of things.
No matter which one we do, it's just gonna fail.
Yeah.
And from someone that has a hard time coding, yeah.
All right, so I got it to work, guys. So if you're having trouble getting it to work, you can try to make these changes, okay? So I think one thing that might be an issue is actually the hexahedral elements. And so if you're having trouble with the hexahedral elements, you can try changing to tetrahedrons, and that should help. Okay. The other thing that you can change here is that you want to make sure that your end time is actually not too large. And so if I go to analysis settings here, I set my end time here to be about 1 millisecond, so 0.001 seconds. Okay. And so if you're having trouble getting these results, and so when you play the animation, it should look something like this. Okay, so your car should impact, and then after that, it should just kind of like vibrate. And so it should just go like that, right? And then the energy summary should look something like this, where you have kind of initial impact, And so the initial impact happens when the kinetic energy dips down, okay? And then from there, it kind of comes back up and then you have this kind of wiggling stuff, right? So the exact pattern of wiggling is gonna look different for everybody. And so it doesn't have to look exactly like this, but as long as it kind of has that general behavior of, you know, where you clearly see kind of initial impact and you have some vibration afterwards, that's what you should be looking for in this project, okay? All right, so play with the settings a little bit. Try to get your car crash to look like this essentially. Yeah, so the hourglass energy is kind of like a fictitious energy. So that's kind of like energy that's stored in a mesh. And so it's a very interesting thing. So I think you saw earlier when I was getting errors, the hourglass energy is shrinking. And that's because, you know, when the impact happened, a lot of the energy was stored in the structure. It was actually stored numerically in the mesh, which is an error. And so it's actually good that the angle tracks up, because if it gets too high, then you know that you have some issues. It should stay kind of control kind of your bottom line. And the contact energy is kind of like, it's like friction. It's like friction in between the parts. Any energy that comes from the contact itself, that's so that should be very close. Yeah, there's something like that. So it doesn't really matter what. Yeah, so you can just use many energies.
Probably 5. We're just playing with the velocity to try to get our own
Exactly.
stress down to 5.
Exactly. Yeah.
And that's like a way of
Yeah. You need to reduce it.
I started I noticed like sometimes like yeah, that's a good question. You go to view oh yeah, wait, Oh, okay, so what can happen sometimes is we kind of make changes to the. And we have trouble overriding it, so somebody has to like this clear. And so, because when you try to rerun this, it tries to kind of run it naturally. Sometimes like there's something. Was it bring anything? Yeah, the best in terms of reliability.
Oh, what's the next side? Because I made mine too, okay. Well, I did, I was too small than that.
Yeah.
But when I went to run, it wouldn't run.
Oh.
You know, so here's the arm.
You said you made a case. Yeah, what was it? Okay. Let's try it again.
Because I had them.
Yeah, we try to. Usually it's more specific, like. Yeah, save it in there.
So I realized.
I dropped it down to 5 and mag, no problem. Yeah, we got
After Thanksgiving. There's a little bit too much going on right now, so. And the final project is basically just a redux of a midterm project, and so there's not that much to go over, it's basically you guys are doing the same thing, and so, I think we're gonna wait till after Thanksgiving. Same thing, but you can choose the jump.
I just did the way of the shot, and I just it overshot.
It's gonna take a few tries.
I'm at 34. I'm getting on close to. So, you know, drop down the first time, that's close.
Yeah, get in there.
3,000 millimeters per second.
All right, so we got about 20 minutes left in class, and so I at least want to tell you guys kind of what's remaining in the activity. So this activity is not very long, and so it's definitely shorter than activity 4. And so there's just a couple extra parts here at the end, okay? And so problem 5, I want you guys to find the maximum velocity of the car that it can handle before it just totally fails, okay? And so what we're going to assume is that we're going to assume that aluminum alloy has a yield strength of 55 megapascal, okay? And I want you to run successive simulations with different starting velocities until you get an equivalent stress around 55, okay? And I will say this, so don't stress too much because these simulations take a while to run, so you don't have to get it exactly 55 on the nose. And so if it's plus or minus 5, then that's fine with me. So something in between 50 and 60 megapascal, as long as you're within that range, you know, don't stress too much trying to get it exactly to 55 because you'll be sitting at your computer for a long time. Okay. Okay, and then problem 6, I want you to just repeat that, except I want you to change the material properties of the car to polyethylene. Okay. So remember from the beginning, we added a second material property to the car, and we're going to assume that the yield strength of polyethylene is 5 megapascal. Okay. And so just like before, you're going to find the maximum speed until you reach about 5. And again, don't stress too much about it. Just get close. Anywhere between 3 and 7 of megapascal will be fine. Okay. And then you have the standard summary after that. Okay. And that's the activity. And so we did the vast majority of it. And so if you've already kind of gotten this far, you can spend the rest of today kind of playing around with the speed. But besides that, you know, I won't keep you guys any further. And so, because I know you guys have a lot of things to study for, a lot of things to do. So I'll stick around until 6:45, of course. But if you guys are heading out, thank you guys for coming this week. Hope you guys have a good weekend. Best of luck studying. I know you guys have a lot to study for next week. You know, I'll be available as much as I can. You know, I have office hours all of next week, so make sure you take advantage of that. If you want to meet outside of office hours, you can always email me. We can set up an appointment. But yeah, it was good seeing you guys, and see you guys next week if you guys are heading out.
55.8.
That's good. That's perfect.
That was the thing with the how much is this? To be fair,
We should reduce them all. Think about it, even if a regular car is going at like 5 miles an hour, it's like, Yeah, so we're gonna. We'll take it back. Technically do, but just for the actually is. Oh, we see this. Why not? I don't, Mondays and Wednesdays I work 8 hours because the game is coming back. Okay, Mondays and Fridays. And Tuesdays and Thursdays. Short. Yeah. Yeah, I'm not gonna like.
Here's the problem. And remember, like the one that's like kind of like a.
Yes.
I tried to put anything that was
Oh, yes, yeah, oh, I forgot the end of that. So 3D is actually the geometry for that one.
Yeah, like that one.
Unstable. And so you put in a map, it's actually it's like a matrix, singular matrix.
It's because two of the things are the same.
Exactly.
Yeah, yeah.
So that one, just worry about setting up the matrix, but don't worry about getting. But the reason it gives me an answer is because I have an old version of that, we got a meeting. And so the tolerances and that one are different than the new version. So yeah, you can just set up a matrix.
One last question then for the last problem that I don't remember. I remember that problem 3B didn't only had answers to the translations, but not the forwards.
Yeah.
If there is, part 4 is the only thing where the teleports, does that mean I don't have to solve for those?
Yeah, again, so just off the.
Like that, no problem.
Yeah.
I put that into Nala and
Yeah, so it's, so the reason, so that this system's actually very, very close to being like the. So, and that's the function. So this one is worried about saying. I was gonna mention today, but I'll send it now. Yeah. Oh, it's, yeah, no, it's just happening. Yeah.
I wasn't sure it was
Yeah.
Oh, 45.
Yeah, I want you to do this. You're starting, so river you're gonna go. And we want to get the angle with respect to the positive x-axis. We always rotate counterclockwise. Get into that position. But the interesting thing is that it's for 350 versus 45. I think you get the same answer. The signs are still the same. Actually, no, you will see some differences. Because the cosine of 315 is the same as cosine 45. But the sine of 315 is so you will see some difference. So 45 is the same as minus 225. Yeah, so 45 and 225. Yeah.
I know you are. Yeah, did you tell your phone? Okay, when you use the bus, oh, you lost it? Oh, you left at the library, huh? Oh, you left it in the house? The library, yeah, I think. How do you go? No, not today. No, I'm talking about the old one. Yeah. You got the new one? I didn't.
Yeah.
So I don't want to reference the projects. So one of the things down here.
So that's the total. So this is the length that you.
Oh.
So the total length. You guys still. Right. So these, so two of them can be less than. But you guys wait. This is. So that's. So what they. More of that. Is well, yeah, I was, but it's also. What I did was it actually could be different. Or depends on the way you like it, but you can use this as kind of like a situation, the way that you. Because if you do it kind of a part of the way of the increase now, it's for sure, but then it's a little bit harder. That's the other. I had that one. And so it's same thing with. So there's things that you can do. So I just have them there. Okay. Yeah. 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 So I want to say like. Oh, sure, yeah. Yeah, so for the activities or the final project, so for the final project, I was planning on because other people have that, but I'll post that as the. So this term was like, I don't know. Okay, yeah, I'll do that for the final, so we'll talk about the final project after the next. Yeah, okay.